So hello everyone. I'm very glad to meet all of you once again. So this session, I would like to discuss uh, statistics in data science and machine learning. All of you have gone through statistics and some probability during your high school level. And in what way statistics connected in data science, and how do you take this idea towards machine learning modeling? So let us discuss. So whenever we talk about statistics, we have two major division in statistics. One is descriptive statistics. Descriptive statistics. Number two, it is inferential statistics. See, in machine learning, at different stages, we'll be using all part of the statistics. For example, when you start doing any modeling, okay, with the data, with the given data, the moment you look at any data in modeling, so we have three different scope in modeling. Number one, with the given data, you can give a description. That is what your descriptive statistics is going to talk about. That descriptive statistics is going to talk about. You describe the data. Okay, you describe the data. So this data is the historical data. Generally, we call it as the empirical data. And any probability analysis you do with the historical data and empirical data, we used to call it as a empirical probability. Empirical, empirical probability. So this is the past data in which a company has generated based on their business process. So their day-to-day business process, they have generated this data. Due to their domain knowledge and experiential knowledge, they have done a lot of decision making based on the historical data. Now the company wanted to move towards a data-driven decision making, right? So, okay, they want to explore this data in a different way. We can explore this data. If a company just wanted what is the quick insights about the data, what is this, what story this last 5 years record or even 10-year data, what is the immediate story you're going to connect from this data? That is a descriptive statistics. For example, if it is about something related to sales data, or it could be a weather data, meteorological data, or it could be a healthcare data, whatever it is, you just describe about the data in terms of summary statistics. So we are all familiar with the 5-point summary statistics. What is the minimum record in a particular variable? For example, if I'm analyzing a healthcare data, suppose you take a column called glucose. Glucose. What is the minimum glucose level? What is the maximum glucose level? What is the mean glucose level? And you can check what is the median value. And other informations like quartiles. Median, we know that it is a second quartile. It is popularly called as the Q2, which is representing the 50th percentile of the data. Similarly, we can also report Q1, first quartile, as well as Q3. Generally, we call this is a 5-point summary. We can, very popular way to visualize this as a box plot. A popular way to. So in my earlier video, the introduction to data science, I have given different visualization techniques, particularly like univariate analysis when we do the bivariate analysis. So this is box plot is this 5-point summary. You can see what is min Q1. This is your median line is Q2. This is a middle line. You can see. Generally, mean is not reflected in the box plot. Q3. So generally, what we say this Q3 minus Q1. Okay, this distance is called as the interquartile range. Interquartile range, and this point will be at 1.5 times of IQR. This distance. This distance will be at 1.5 times of IQR. So we call this as inner fences. And another 1.5 times of IQR if you travel either to the top as well as bottom here, we call it as the outer fences. According to the different domain, people used to set the boundary. The very popular boundary for the outliers is any value, any data greater than 1.5 times of IQR. They used to call it as the outlier or extreme values. Some business problem, these extreme values could be the information. Okay, it could be the some vital informations. Could be a pattern. I could call it as a pattern in which you need to preserve that detail. You should not remove it. In certain business application, if those values are noise, you can treat that outliers as a noise due to data entry error, or if the sensor has picked that data due to wear and tear, it is a wrong data entered into the model. So if you treat that extreme value as an outlier, definitely that outlier has to be treated. So you, from the given data, you are going to give the complete summary about the data, empirical data. What is the average glucose level? And maybe if I have a gender, another column, you can give whether the glucose mean value changes with respect to gender. Okay, you can give the summary statistics, gender wise you can give. For example, if my summary statistics give me a category wise box plot when you analyze, this is for male and this is for female, you could visualize, okay, the average glucose level with respect to male and female, is there any difference is there? So either as a univariate analysis like or a bivariate analysis, this is completely going to give you the visual description about or visual inferences about the available data. We can also sometimes call this as a sample data. Okay, we are not going to comment anything on the population data. Whereas the inferential statistics, okay, it is going to deal with the given data, with the sample statistics. We call it as the sample information. We are going to infer something about the population. That is what your inferential statistics is going to deal with. So with the given sample, we can infer the population parameter. So let me give a larger picture. Okay, let us assume this is a population or production data or population data or the future data, whatever you can call it as population data. There are certain terminologies attached with population data we should be aware of. Generally, the sample data, I used to collect some random samples from the population, and whatever the variable I have collected, that variable, that is for example, if the variable is a quantitative variable, quantitative in the sense, for example, age, glucose, body mass index, these are all the values of quantitative variable. Or I collect a qualitative variable, like a categorical variable, like a gender, or whether the person is a smoking or a non-smoking person. So a category could be 2, or even how many kids are there, 1, 2, 3, these categorical variable. So I can analyze either quantitative variable as well as a qualitative variable. Accordingly, the analysis procedure will change. And of course, the probability distribution will change naturally. So there are certain terminologies we should be aware of. Pertaining to the samples, we use the variable x bar. Let me talk about continuous variable, right? X bar. And population, it is used to refer as mu. And the sample standard deviation I used to specify is a small letter s, and it is a sigma. And the variance of the sample is represented as square, and here it is a sigma square. And we used to represent small n to define the total number of samples. In population, I used to call capital N. Okay, these are all the terminologies. With the sample data, okay, with the empirical data, with the sample data, collected data, anything we can infer for the future about the population data. Okay, we can predict mean value of the average sales in the future. Okay, we can do the inferentials by doing inferential statistics. Okay, we can predict for the future data. We can do a statistical inferences as well as we can go with the machine learning model. Subsequently, I will discuss the differences. One is the statistical learning, another could be the machine learning. So in the statistical learning perspective, we call it as the inferential statistics. From the sample data, how do we infer the population data? Or how do you prove statistically, how do we verify statistically whether the sample mean is the representation of the population, whether the sample mean is the representation of the population mean. So we can do the estimation, right? Here I'm going to use the word estimation. I'm going to estimate the population parameter mu from the sample mean. So technically, nobody can precisely estimate mu. Okay, definitely that point estimate is practically impossible. So what is possible is the range estimate. We can do the range estimate. I can give a range estimate. So this range estimate, whenever we talk about this range estimate, we used to discuss about confidence interval and other stuffs like this. What range you are going to estimate, you are going to represent your estimated mean, what range you are going to present, whether 90% confidence interval or 95% or 99. Okay. So all those things down the line, I'll be discussing in detail. So now you should understand the scope of inferential statistics. What is the scope of inferential statistics? From the sample data, we are going to infer the population. Okay, that inferential parameter can be a quantitative variable, mu. If it is a qualitative variable, I can infer the proportion. For a quantitative variable, I can infer the mean. So that is the goal of inferential statistics. In machine learning perspective, okay, in machine learning perspective, I'm going to tell you these three goals. In fact, we have discussed two. One, number one, you just give the visual insights about all the available data. Okay, visual insights in terms of histogram. Okay, in terms of density plot or histogram, or it's a univariate analysis. In terms of a box plot, you analyze the variable. For a quantitative variable, if it is a qualitative variable, you analyze in terms of bar plot or pie chart. Okay, about pie charts. And for bivariate analysis, you analyze in terms of scatter plot the relationship between two variables, dependent and independent variables, or between two independent variables, x1 and x2. What's the relationship? All those things. So this is a completely visual insights about the available data in hand. Okay, empirical data. What story your last 5-year data or 10-year data tells you. So what is the relationship between two variables? And what is the characteristic of the individual variable, whether the variables are normally distributed or it's a skewed distribution, and also we can analyze the 5-point summary in the box plot. your bar plot, your pie chart, your scatter plots. So this is your complete summary about your data, right? Number two, that inferential statistics can be extended in machine learning as a prediction model, right? So I can establish a relationship between, okay, my outcome variable y as a function of various independent variable like this. I have p independent variables. For example, I can predict blood glucose as a function of, okay, as a function of age. It could be another variable like weight, and another variable I could use body mass index, okay, and smoking habit, yes or no, qualitative variable, whether the person is doing exercise or not. So my data can have a quantitative variable like this and a qualitative variable like gender or smoking, non-smoking, doing exercise regularly or not. Based on these variables, I can relate some kind of relationship between y and x. That relationship, if I use a linear model, it becomes a linear models, like a regression, linear regression. Also, I can have a non-linear relationship also I can establish, provided if these variables are maintaining a non-linear relationship with y. So we can go for a non-linear models. And basically, this machine learning model learns from this data in terms of model parameters. Okay, using this model parameter, we can use it for predicting for the future. In future, there is a new patient with so and so information, like this age, with this weight, with the height, and this much body mass index, and with the smoking habit and exercise habit, and so many parameters, independent variables. Our machine learning model can predict for the new incoming data what is the predicted glucose value. Okay, so that is the goal of any machine learning model. So we call it as a prediction model. So number two goal is a prediction. Number one goal is a description, describing the data. Number two, second goal is a prediction. Prediction, you establish some kind of relationship between x and y. Number three, prescription. Prescription. Okay. Suppose if I have a linear relationship between x and y, and you can prescribe, okay, to maintain a healthy glucose level. Okay, to maintain, for example, once you developed a model parameter relationship between x and y in terms of model parameter, if it is a linear regression, beta 1 time of x1, beta 2 time of x2, and so on, you establish a linear relationship like this, and you have built the linear regression model. You can also do the inference, actually. That inference is what the prescription. So such prescription is possible only for the linear model. Of course, it's not possible for non-linear model. So non-linear model, the inference is we have to trade off with the inference. So we can prescribe to maintain a healthy blood glucose level, how much of weight you should maintain, how much of body mass index you should maintain. Okay, to maintain certain, for example, to maintain 180 milligrams per deciliter of blood glucose level. So you can prescribe what should be the ideal weight and height, BMI. So you should maintain exercise and so many other parameters we can describe. You can also prescribe. That is a prescription. So once you establish the model equation as a prediction model, okay. So you can use it as a for the future records, incoming records. You can predict what is the glucose value. Also, additionally, you are doing inferences because since it is a linear relationship, that inference is represented as a prescribing. So for the so and so y value, how much of x1, x2, x3 and all you need to maintain, okay, to get this y value. That is a prescription. So different business problem will expect different goals. Some of the business problem will expect only description level goal. Some business problem would expect prediction as a goal. Some business model would expect additionally the inference also the goal, prescription as a goal. According to the nature of the business requirement, we need to wisely choose what task we are going to perform with the data. We have to decide. Okay, this is a no your prediction, whatever the prediction you are doing, the model we build as a machine learning model in analogical to the statistical inference. Okay, okay, going back to our the basic statistics discussion. Okay, I'm just giving this is the broader picture. So the main agenda of this session, this particular session, I would like to focus on the basic probability related to our inferential statistics. So probably the moment we think about probability, all of you are very familiar with very classical probability. Classical probability. What is this classical probability? Right from the school days, we are very familiar with well-defined sample space while tossing a coin, fair, unbiased coin. So we have a chance of getting a head and tail. What's the probability of getting a head? Is 1 upon 1 chance out of 2 possible outcomes. The probability of tail 1 by 2. Because the sample space is well defined. Even for throwing a dice, so we have these are the outcomes 1, 2, 3, 4, 5, 6. Throwing a dice is an experiment and you're getting whatever the value, this is the outcome. What's the probability of getting 5 when I throw a die? So we have 1 chance out of 6. So probability is the classical probability, pack of cards, 52 cards. In a pack of 52 cards, what's the probability of king randomly picked? King, yes, we know. So king we have in 4 flowers, we have 4 kings. So 4 upon total cards of 52. So what is the probability of occurrence of king upon the total outcome? So these probabilities are considered as the classical probability. So well-defined sample space we are familiar with. The second type of probability is what just now we have discussed, which is very practical oriented, which is an empirical probability. Empirical probability. Generally, it is a historical data in which over a period of time, what the data we have generated. Number 3, it is a subjective probability. There are certain applications in which we don't have a prior data. Okay, there is some rare field in which we don't have some prior data, which is not digitized or recorded. Sometimes we need to seek the domain expert. There is an expert who was in the field for the 20 to 30 years, a domain expert. Their experiential knowledge in that particular domain, whether it could be the very rare cancer type of cancer. He's an oncologist. It's a very rare disease and a rare cancer type. And he's a domain expert for the last 2 decades. He was very well versed in handling those cases. And there is a person who's very well exposed in predicting weather. Okay, is a meteorologist. Whatever the irrespective of the domain, we have different subject matter experts, domain experts. We could utilize their experience in arriving certain probability, prior probability, to get some idea about prior probability. If in a case where we don't have any record, empirical data, we don't have, definitely we can seek the help of subjective domain expert to get some idea about what is the prior probability. So this is how we broadly categorize probability into three major types: classical probability, empirical probability, and subjective probability. So mostly in our practical data science applications, we strongly depend on these two. These two. As once you completely understand the entire spectrum of data science and machine learning spectrum, you could appreciate how this empirical probability and subjective probability are in use. Now let us discuss in probability, there are certain operations we perform. So I would like to broadly divide those operations into four major categories like this. Four cases. First, I would like to call it as a mutually exclusive event. Let us discuss what is mutually exclusive event in probability theory. Whenever we deal with mutually exclusive event, let me consider two events A and B. Okay, A is one event, B is another event. What is the meaning of mutually exclusive event? They cannot occur at the same time. For example, when I'm getting a head, definitely I may not get tail simultaneously. Okay, if a person is a diseased person, same time simultaneously he cannot be a healthy person. So king means, if what is the probability of picking a king means you are simultaneously you will not pick a queen. So king and queen are two exclusive event. Head and tail, head or tail. Any one at a time is going to happen. For such mutually exclusive event, is represented in terms of what is the probability of, because they are exclusive, either A is going to happen or B is going to happen. What is the probability of an event A or B? This is how a mutually exclusive event is defined. So this could be represented as probability of A union B, because there is no commonality between these two events. Since they are mutually exclusive, probability of A union B, probability of A plus probability of B. When tossing a coin, what is the probability of getting a head or tail? So 100%. Probability of head is 1 by 2. Probability of tail is another 1 by 2. 1 by 2 plus 1 by 2. You get 100% chance. Either the head is going to happen or tail is going to happen. So what is the probability of picking a king or jack? If I ask you, what is the probability of picking a king or jack? So we have 4 king in a pack of cards, 4 out of 52. We have 4 jack in a pack of 52 cards. So this is the this is the total probability. What is the probability of picking a king or jack or queen, whatever it is? We should understand when I'm picking a king, definitely I cannot pick jack, right? Okay, when I'm going to get a head, definitely I'm not going to get a tail. Such probability, such events are considered as a mutually exclusive event. Whenever you are dealing with those probabilities, we should sum up those values. A or B, A union B. I'll give another example. Mutually non-exclusive. Let us see what is mutually non-exclusive. We are going to extend this idea for the mutually non-exclusive. Whenever an event A and B, the two event, which is said to be mutually non-exclusive, means there is certain portion of commonality exists between A and B, right? That is an idea here. That commonality I need to subtract from this P of A plus P of B. That common aspect, whenever you find a common aspect between A and B, that common aspect can be removed in the form of an intersection point, right? So in this case, how do I define my probability of A union B here? Here A and B are mutually non-exclusive. Here probability of A plus probability of B minus probability of A intersection B. This A intersection B is a commonality. For example, even in the same example, pack of card example, if you see. Suppose if I say jack of dice, what is the probability randomly picked card is going to be the jack dice? So here the jack and dice, jack is one event and dice is another event. Okay, jack is one event, dice is another event. There is a commonality that jack of dice is a common aspect, right? When I pick a card, that card is going to be the jack diamond. So what is the probability of jack? We have 4 jack out of 52. What is the probability of choosing a diamond card? Out of 52, we have 13 diamond cards, right? 13 diamond cards. So we have one jack diamond. So that is the common aspect that has to be subtracted from this. So if you simplify, we get 16 by 52. 30.7%. So such event is called as mutually non-exclusive event. So both you are calculating P of A union B. So here additionally I subtract that common aspect between the two events. That common aspect should be subtracted from P of A plus P of B minus P of A intersection B. Okay, this is one set of case. The another set of cases of more practically have a lot of relevance with respect to statistical learning and machine learning. That is what we are going to discuss. A mutually independent event and mutually non-independent event. How do you appreciate this difference with respect to the earlier cases? If you look at the earlier case, the crucial difference is what way I can differentiate independent and mutually exclusive is. In mutually exclusive, the sample space is common. If you notice the examples, whatever we have discussed, event A and B, for both event A and B, my sample space is head and tail is a sample space. Choosing a jack or a queen, my sample space is 52. My classical probability sample space is common. Whereas in the independent event, Okay, my sample space is different for both the events. That is a crucial difference. That is why we call it as a mutually independent event. Mutually independent event. So that means those events can occur simultaneously, but the occurrence of one event will not influence the another event. That is the point you should understand here. So they are mutually independent event. Okay, the occurrence of A no way influence the B. In contrary, we are going to discuss non-independent events. Non-independent event. The occurrence of A, which is going to give an impact in occurrence of B. Okay. So that is the different. First of all, we should understand in what way independent and mutually exclusive events are different. In mutually exclusive events, we have a common sample space, but here we have a different sample space for event A and event B. It means they can occur simultaneously, but one event is not influence the another event. Let us take an example so we can appreciate this. Assume that you are a student, you are staying in hostel. Assume you are a student, you are staying in a hostel, and you have a daily pattern, certain event. Let us consider one is the probability of you make a phone call to your parents. What is the probability that you make a phone call to the parents? So based on the empirical data, based on the last 365 days pattern, okay, I establish what is the probability of making a phone call. It's a one event in an independent event. Let us say 80% of the time you make a phone call to your parents. For example, every 10 days you make a phone call on 8 days. Okay, 2 days you missing out. So almost every 10 days you make 8 days you make a phone call to your parents. Another event I'm going to take, you're doing exercise every day in your hostel room. Okay. So someday you do an exercise, some other day you skip the exercise. Okay, exercise. No. You may think, okay, because of exercise, the student is not getting time. That's why he didn't make a phone call to the parent. If you have that thought, let us define a problem very clearly. Okay, all the phone calls, let us assume we'll make a condition. All the phone calls he is making in the evening. Okay, in the evening hours. And exercise he is doing in the morning hours. Okay, to rule out the condition, you might think that since he is doing exercise, he isn't getting a time to make a phone call. One event is influencing another event. Okay, to break that question. Okay, let us assume all the phone calls he's making in the evening and exercise he is doing in the morning. So mutually, we are defining our independent event. Okay, we are justifying the events are independent. This is how we justify. Any example you can take, whichever the one event is not influencing another event. So his historical data says that 60% of the time he is doing exercise. Every 10 days he does exercise on 6 days. So if I ask you to calculate what is the probability of both the event, occurrence of both the event. So both are independent event. What is the probability that the occurrence of what is the probability that the both event A and B is going to happen? A intersection B, right? Is defined as for the mutually independent event. It is a product of event A into. Definitely, we know that what is the probability of making a phone call to his parents is 80%. What is the probability in a given day he's doing an exercise is 60% based on his last 1 year pattern. What is the probability on a particular day he's doing exercise as well as he's making a phone call to his parents? definitely that probability will come down, right? So what is the together probability here is 0.8 into 0.6. So 0.42. Okay, it's just 42% chance on a given day. Okay, 42% chance on a given day he's making phone call to his parents. At the same time he has did exercise in his room. So this is a probability of combined probability of the two independent event. This case is more interesting. Okay, this case leads to a conditional probability, in fact. In similar notion, if I write equation here, what is the probability of the two non-independent events? Okay, A can influence B. What is the together probability, that is A intersection B, probability of A? Let us assume the probability of A event is already happened. This B event is going to be influenced by A event. The B event is going to be influenced by A event. So that is why the A event is going to influence my score P of B. So this P of B bar A representation is called as, in probability, we call this as a conditional probability. We call this as a conditional probability. So either way, suppose if a B event is going to influence the A event, so first B event has occurred, that is going to influence the A event, probability of A bar B. Either way we can write. So very practical example, we can think of a lot of practical day-to-day life example. For example, one event is influencing another event. For example, A event is like you get up late in the morning. Okay, you get up late in the morning. And B is an event that you are reaching office late. You're reaching office late. Naturally, one event will have a ripple effect on another event, right? There are certain days, your historical data could say that there are certain days, though you woke up late, but you managed to reach office on time. There are exceptional days, definitely. But what your historical data tells that most of the time, whenever you got, let us say we have historical data says that 80% of the time, whenever you got up late, 80% of the time you were late to office. So definitely this A is the event is having a strong impact, influence the B event, right? So we have a statistics of last 365 days. How many days you got up early, and how many days you reached office on time. On those days you got up late, how many days you were late to office. If we have those data recorded, obviously we can pick up those information and we can key in and we can calculate. Okay, what is on a given day, what is the probability that you woke up late and you're reaching office late? You can calculate the combined probability based on this formula. It's a conditional probability. So the conditional probability, from the conditional probability, actually we got a very interesting and very crucial definition in statistics theory, Bayes theorem. This Bayes theorem, the Bayes rule, is basically evolved from this conditional probability. So in the next discussion, in the next video, I'm going to talk about how Bayes theorem, Bayes established a relationship in this conditional probability. Actually, he is just trying to establish a relationship between probability of A bar B and probability of B bar A. How that relationship is going to play a crucial role in prediction. In fact, This is it's a mother of all the machine learning model, including the deep learning model today, what we discussed. The very important foundation was given by Bayes theorem. If Bayes theorem was not there, okay, Bayes theorem is not there, today we cannot enjoy all the sophisticated prediction models, including the deep learning. So this theorem is what we are going to discuss in the Bayes theorem, and it's going to lay a very foundation and the idea. In fact, the very first uh, automation prediction in most of the email, the spam filter, right? We are very much familiar with the spam filter. The spam filter automation, that was a very basic prediction uh, rule established for the spam filtering was successfully done with the Bayesian prediction logic. So in the next video, I'm going to talk about how Bayes theorem is used for uh, a prediction rule, and with a small case study example of like a spam filtering, how exactly the spam filtering works based on this Bayesian logic. In fact, most of the inferential statistics, statistical learning, the foundation and the inspiration got from the conditional probability and the Bayes theorem. So that's why I told you the most of the data science, practical data science applications, mutually independent event and mutually non-independent events are playing a huge role. Basically, purely these data, these informations are collected from the empirical data, right? We are collecting these informations from the empirical data, from the historical data. So from the historical data of how a student, how a person is uh, making a phone call and doing exercise pattern. Even this example, you see, for the last 1 year pattern or last 2 year pattern, we collect the information. Based on that, we infer on the future. So lots and lots of examples I'll give you when I start discussing about a lot of problem with conditional probability in the next video. Okay, today I stop the discussion with this. So as a summary, what are the things we have discussed today? So my main intention is to introduce probability and statistics. It is going to be the series of lecture. The subsequent videos, I'm going to talk about probability and statistics, the role of probability and statistics in machine learning, in AI as a general bigger picture. So here I just introduced what is the differences between the statistics, descriptive statistics, inferential statistics. In fact, it's a prescriptive inference goal. So description, descriptive, actually this is a prediction model, and prescription model. Prescription. Then I moved on to discuss about the type of probability. That is classical probability, classical, empirical, and subjective probability. And what are the calculations we perform in what is the nature your events can be, whether your events are mutually exclusive events, what kind of calculations you can perform, either A or B, how to address this. Mutually non-exclusive, once again A or B, how to address this. So both are A union B. So probability of A plus B, the only difference here is P of A plus P of B. Here it is P of A, P of B minus P of A intersection. We have to subtract this common aspect. Number 4, mutually, it's an independent event and non-independent. Here the sample space is common for both A and B, whereas the independent event, we have a sample space are different. Here it is a common. In mutually independent events, sample space are different. So A and B occurrence can possible. Simultaneously both occurrence is possible. That is why, and since simultaneous both occurrence is not possible, that is why this or this. So mutually independent and mutually non-independent, both the cases simultaneous occurrence can possible. So that is why A and B, we talk about A and B means intersection. Both the case it's product P of A into P of B, but only difference is in the second case since it is one event is going to influence another event. So when I take a probability of B, the event A is going to influence B. So I take this. So this is a quick summarization what we discussed today. In the subsequent class, I'm going to talk about more in detail about this conditional probability and its importance in Bayesian theorem. Okay, thanks for watching. We'll meet once again shortly in another video. Okay, have a very good day.